Hi, welcome, good morning. Great to have you here. We will make this a very cozy session on showing you around in our DISHA AI initiative. I am here with Rito and Krishna. I'll introduce them in a second. But please, since we are all here in this room at WSIS, please ask any questions that you might have, and let's use this as an opportunity to exchange and get a fantastic teach-in from the colleagues that we have here. We are day 4 of a week that has been super packed with everything around AI. And from our perspective, walking around, having so many conversations, we really see that there is so much tremendous momentum, interest, attention on the topic. And we are always asked at Global Pulse, like, what are the things that are actually working? Like, where can we go? Where can we look to see, like, what are the examples of using AI? And I'm super happy that we have one with us today that we have built over the last few years into something that does work and is an interesting blueprint from both a technical and partnerships perspective. My name is Talia von Lubin. I'm the portfolio manager for UN Global Pulse, which is the Secretary General's Innovation Lab. And I have with me Rado, who is the tech lead for data insights for Social and Humanitarian Action, in short, DISHA, and Krishna, who is a senior software engineer and tech lead at Google Research. And needless to say, joint session by 2 of the DISHA partners that you will learn a little bit more about. Our plan for this next hour is to give you a brief overview of what DISHA is, what we are doing with AI and with AI partnerships. And then we will make this quite interactive with demos of the technical details and the technical solutions that we have been building. Rita will lead us through the DISHA product suite, and then Krishna will show us some things about Google's Earth AI model that we are using and embedding in some of the work that we are doing for the UN. So let's get started. DISHA is currently very focused on humanitarian response. And many of you know that every year around 300 million people require humanitarian assistance. At the same time, especially over the course of last year, we saw an incredibly dramatic reduction in the funding and in the resources available to bring humanitarian response, and at the moment we see only a small fraction of the funding appeals actually being met. So the direction is clear. We do need to do more with less, and for sure AI provides one key opportunity and one key enabler to do exactly that. So imagine after an earthquake like the one in Venezuela just now, or after cyclones or hurricanes, what humanitarian responders and UN entities are very often doing is they provide food, shelter, immediate relief funds after a disaster hits. And AI can help us with directing this support in a much more targeted way. With satellite imagery and AI models, we can now, today, do what needed sometimes weeks to find out where exactly is the damage happening. We can find out this information within hours or days. And DISHA is not just about finding and building an AI model. When we started this whole thing, we realized that the UN might never be the strongest organization to build your cutting-edge AI model. And at the same time, we are also not the ones who have access to the satellite imagery. We might not even be the ones who are who are bringing the humanitarian response. But we can be a platform for bringing all of these together. So we like to think about this whole data and AI and humanitarian response as a complex puzzle where you have people who have the data, people who have the funding, people who bring the response, people who have the technical capabilities and knowledge. And we have been building a machinery to bring all of these together into very concrete use cases and use the strongest AI models that we find out there for the most dear causes in humanitarian response. Just briefly flashing up, very tiny logos. You might need to come a bit closer. On with whom we are working on this right now. So I've mentioned it's a number of key technology partners, making sure that we are in the loop with new AI developments, and we'll hear a little bit more on what we are using at the moment on from the Google research side. Then we're working with data providers to give us access to key data to feed the models. And then, of course, a number of implementation partners. It's surprisingly hard to find the sweet spot of where you can use a model and where you can find those entities and those teams who can then bring this into action. So that's what the team is doing. And I actually won't take a lot more time before we are diving into that. The first set of solutions that DISHA has developed where we want to focus on today is all within this humanitarian response space. And we are very proud that within the course of last year, we build this out into something that's being adopted, being used by very different teams, both within the UN and outside of it. And Rito, I'd love to invite you over here to take my seat and show us around a bit on what exactly that looks like and what DISHA Solutions can do today.
Thank you so much, Talia. Hi and good morning, everyone. So I'll take it over from here to show you some of our flagship products in this area. And one of the first products that we launched, we refer to as socio-economic mapping, and it is currently operating already in the Philippines. Philippines is a country that experiences about 20 typhoons per year, which it displays so many people, and sometimes for a few days, sometimes for much longer. And in the Philippines, we brokered UN's first evergreen data sharing agreement with one of the largest telco companies there called Globe Telecom. And they give us access to this amazing anonymized data about their mobile network usage data for 50 to 60 million people, and it is refreshed daily for this purpose. And we built a solution to analyze this anonymized data within the environment of the mobile data provider itself and extract and share standardized aggregated insights with authorized humanitarian users only. And to access these insights, none of the humanitarian organizations had to negotiate any bilateral agreement with Globe because they do not access the raw data itself from the telecommunication company. They access only the final insights that we give to them through our DISHA dashboard. Okay. Okay. So this is one of the screenshots from our DISHA dashboard for the socio-economic mapping, or SEM. So analyzing this mobile network usage data allows us to color code the map in the Philippines up to village level, highlighting areas that are likely experiencing abnormal flow of people movement, either inflow or outflow of people. And we're also able to estimate poverty levels from phone through their activity of top-ups, balances, and also the usage of SMS and calls and mobile network usages. And the humanitarian organization can access this color-coded map every day of the year. And we also pull together a few fact packs of them, like in an ad hoc way, in a report that is easy to digest for them, following an immediate emergency situation. And these insights help make decisions about where to send aid. So for example, on this map, you can see that there are like some different colors. So these colors highlight different kinds of anomaly in terms of people movement in Philippines. So red colors here indicates that there are many people moving out from that area after a disaster, and green colors indicates that there are many people moving into that area after disaster. And this might indicate that many people are looking shelters out of the red areas to the green areas. And this kind of information is very useful for the humanitarian agencies on ground to really make decision on where to send help as a top priority. Okay, so the next one is our product called AI-assisted damage assessment. So the question is that after a disaster, so what's actually still standing? Where are the damaged buildings? And humanitarian agencies need to understand quickly as possible, the extent of the damages and the locations. So previously, whenever there is a disaster, like earthquakes or typhoons, so UN Satellite Center analysts had to manually see this kind of satellite imageries that you see in the slides, comparing pre and post images and see where the damaged buildings are located. And this is really labor intensive, it's very time consuming, and often done under a really extreme time pressure. So what we have done from DISHA is we have leveraged Google's proprietary as well as open source models to build and test a product that helps reducing the time needed to do that kind of analysis. So from days to sometimes weeks, or even sometimes weeks to just a matter of hours. So I'll walk through this process one by one. So we have three main processes of this damage assessment system. The first one is the identification of building footprints using Google Earth AI Open Buildings model. And this first model is developed by Google, licensed to us pro bono, to help us identify where the buildings are located on an aerial image from a satellite image like this one. So as you can see on the left is like a kind of input of this satellite optical image. And on the right is like a typical output of this image. So as you can see that the model highlights the location of the buildings by surrounding it with red boxes. And this is very useful for us to get to the next step, which is to map the areas with heaviest damage using the sky model. So this is the second from Google's model, which helps us produce this heat map with like very red areas representing the most damaged buildings, and this helps prioritize where to send help on the ground. So lastly, to produce a detailed assessment, we have expert analysts label a few hundred examples of the damaged and undamaged buildings to fine-tune the model, because as you can see, as you understand as well probably, so many buildings all around the world are not the same. So buildings in the United States, in Geneva, in Southeast Asia, from the roof they might not look the same. So sometimes we need to really help guide the model to really understand the situation on ground. So this is like in some certain countries with different contexts. So that's why we need this labeling from an expert to help guide the model to reach a better results. So as you can see to the left is actually a result from an expert annotation. Red dots indicates the damaged buildings and yellow dots indicates potentially damaged ones. And on the right you see the output of the fine-tuned model after it gets guided more by the annotation from the experts. So the exciting result that you can see from this slide is that this shows 7 times expansion of the visible analysis area compared to the just manual human annotation. And at the same time, 6 times faster processing times compared to when it's done by human. And this result has been rigorously validated by UNOSAT experts and is cleared for operational uses. So as you can see in this image here, compares the assessment of damage left by Hurricane Melissa last fall in Jamaica. And the two zoom-out assessments were produced by analysts from United Nations Satellite Center and Copernicus Emergency Management Service against the output of DISHA damage assessment solution. So to the left is expert analysis, to the right is DISHA. So you can see that there is like high level of agreement here. Mathematically, we can like compute the R2 score, measuring the degrees of likeliness between these two results. And the result is very high, like 0.91, and it's really suitable for operational use. So both the socio-economic solution that we saw before and this one, the damage assessment, is now being used actively by humanitarian response planning and is open to all humanitarian agencies free of charge. So just last year itself, these were used during 11 emergency events, which impacted more than 15 million people. And now I'll show you, other than these two products, we also have just released another solution called refugee settlement mapping, which extracts footprint from satellite imagery to understand where settlements are located, where are the buildings located, and how big of an area the buildings cover. So accurate settlement maps are very critical for effective aid delivery, but are impossible to keep up to date with manual mapping process, because typically you need to send someone to go to the area, really check one by one whether the buildings are still there and how much of an area the buildings are covering. So the last effort to map 50 major building settlements took place 4 years ago, and it took a team of 4 to 6 analysts for 14 months to complete. So it can be very labor intensive. So with our solution, which is powered also by Google Earth's AI Open Buildings model, so we can do this like in a matter of hours and even minutes. So in partnership with UNHCR and UN Satellite Center, DISHA's AI solution will be used to map UNHCR support settlements for the first time, enabling this settlement mapping to be repeated regularly without much human intervention. Okay. So, DISHA is designed to support humanitarian decision making, but we are very clear that data AI should never operate on autopilot by itself. So we are committed to responsible use of data and AI. First, we keep human experts in charge. Every assessment is reviewed by expert analysts before it is used to inform action. We also make sure users are trained and understand the product's limitation, so insights are interpreted carefully and responsibly. Second, access is strictly controlled. So DISHA insights are shared only with authorized humanitarian users for humanitarian purposes only. There is no commercial use, and we apply strict access controls to make sure sensitive insights reach only the right people. And thirdly, we apply privacy by design. So that means we set a really high bar for anonymization, privacy protection, and responsible data handling from the beginning, not as an afterthought. So our approach follows a UN principle for the ethical use of AI. So to close my part, because before I hand it over to Krishna, there are 3 concrete ways you can partner with DISHA. First, if you have relevant data, models, or compute, DISHA can serve as the entry point to share those with us, with all the humanitarian sector. If you're a humanitarian organization, you can sign up to get access to DISHA's current and future solutions. And if you are a funder, your support can help us scale existing solutions to more humanitarian organizations and co-design new AI solutions for emerging needs. So we are always open for new use cases. Okay, so that is all from my part, so I'll hand it over to Krishna. Thank you so much.
Thank you, Raditya. Hi, everyone. My name is Krishna Sapkota. I'm a senior software engineer at Google Research. And I'm a tech lead for the Open Buildings project. So today, I'm going to be talking about mainly 2 things. The Open Buildings project, Sky for damage assessment, and I'll give a sneak peek into Google Earth AI that we released last year, and what that might mean for the future of disaster response and planning. So Open Buildings is a project within Google Research that aims to map the buildings of the Global South. So at a high level, what we do is we train an AI model to automatically detect buildings and their exact footprint outlines from high-resolution satellite images, and we run this model at a continent scale using Google's vast collection of satellite imagery and compute, and these polygons that we create then goes into this Open Buildings dataset. The dataset is open access. It provides researchers, NGOs, and governments with the kind of the foundational data layer needed for a range of downstream applications like vaccination planning to disaster planning and response. So you might ask, why did we set out to map the buildings of the Global South in the first place? So this project was actually born in Accra, Ghana, We have a research lab there, and so this was one of the motivating examples. So here on the left-hand side, you see a satellite image of a location in Cape Town, South Africa. On the left side, you see what looks like a township, and on the right-hand side, you see a relatively wealthy neighborhood. And on the right side of the slide, you see the OpenStreetMaps of the exact same location pre-2021. And this is before our project got started. And as you can see, the township is completely unmapped, right? And we thought, okay, this is problematic. We have to fix it. So there are also many countries, low and middle income countries, especially in the Global South, that haven't had census in decades. Some noteworthy examples are Democratic Republic Congo and Somalia. So Somalia had its last census in the 70s, if I'm not mistaken, and DRC, yes, DRC in the 80s, and this seems to still be true as of last night. I checked, and this is hugely problematic, because it means that in many parts of the Global South, we lack the very basic piece of information, like where do people live, what's the population size, what's the density, and so on, right? So mapping is also very crucial for disaster response. Here you see an onion model that is typically used in humanitarian relief after a disaster. So first you need to know where people live in the disaster area, and after that you need to know of these people who are the ones impacted, and then of these people who are the ones that actually need aid, right, and so on. And if you get this outermost layer wrong, then everything else is just like a blind guess. And the consequence of that is your relief effort is compromised, leaving unmapped and vulnerable people in need, cut off from the much needed aid. So I hope I've convinced you why mapping is important. So now let's look into some of the challenges of detecting buildings from high-resolution satellite images. So the main challenge, the main challenge in the Global South is twofold. One is the diversity of the buildings in the Global South, and the second one is density. Buildings look very diverse in the Global South, and often in areas like slums and refugee settlement camps and so on. The buildings are very densely packed, and that makes it really hard for the model to detect these buildings from satellite images. And also, as Rita mentioned, buildings in the Global South look very different than buildings in the Global North. So if you actually use a model trained on the Global North to detect buildings in the Global South, well, no surprise, it's going to fail, right? So now let's do maybe a quick game, like the annoying CAPTCHA game. So please raise your hand if you think the satellite image tile 1 has any buildings in it. Okay, couple hands, 3 hands, 4. What do you think about 2? Okay, nobody's like building. Okay, 3. Few hands, yeah. 4, especially the one in the red box. Okay, a few more hands. Okay, so let's find out. So none of these are buildings. So the first two are, they sometimes, so these are vegetation and rocks, and sometimes they look like buildings from above. The vegetation one, for example, it could be a thatched roof, right? And also it looks like there's some kind of what looks like roads in between these kind of blobs. And also shipping containers, because they're rectangular, they might look like buildings from above. And the one on the bottom right, it just it looks like a compound, a building compound, but it just walls. It actually doesn't have a building. So these things actually make it really hard for the model to detect buildings at scale. And yeah, well, what might look like a very simple task is actually, if you want to do that at a continent scale, it quickly becomes very hard. And as a result, you need a lot of very high quality training data. So yeah, before we dive into how the dataset was created, let's first maybe get an overview of what the dataset contains. So by the way, if you scan this code, it will take you to the dataset homepage. As I mentioned before, the dataset is open access. It contains 1.8 billion building footprints, so building polygons across Latin America, Caribbean, Africa, South and Southeast Asia. We ran our model on 58 million square kilometers of Earth's surface, and that is roughly half the world's population, half the world in terms of population. The data set comes with a very permissive dual license. So it is licensed under Creative Commons and ODBL. So initially we only had Creative Commons, but we added ODBL to make it possible for our data to be ingested into platforms like the OpenStreetMaps. And from a product impact point of view, since the launch of the project, we now have, in Africa alone, 5 times more buildings on Google Maps. So yeah, this is the homepage. If you're interested, you can download the data directly from the homepage. You don't have to sign up or anything. And you can then use that data and upload that into a GIS of your tool to run any downstream applications like analysis and so on. And you might ask what happened to this location in South Africa. So this is before, right? And so after we released the data set and that data was ingested into OpenStreetMaps, this is what happened. So now this area has a lot of buildings. Yeah, mission accomplished. So let's now look into how the data set was created from a technical point of view. I'm going to fly through the technical details, so please raise your hands and ask questions if you want more details. So we all know that AI is only as good as its training data, so we had to label a lot of data, very high quality data. So we labeled about 200,000 imagery tiles in a dense manner. So that means in an imagery tile, we labeled every single individual buildings. So basically each polygon, right? You draw a polygon like dots around a building. And as you can imagine, it's a very laborious task. So depending on the density of the tile, it can take from a few minutes to hours, if not days, to label a tile, a single tile. And obviously you have to iterate on this annotation exercise to make sure your data is of very high quality. From a model point of view, we use this vision transformer, VIT architecture. Those who might be familiar with it, the task itself is a simple semantic segmentation task. That means that the model takes as input an image and outputs for each pixel in the input image a binary label. So building, no building. So as you can see, input is the image and the output is this so-called this binary mask. We then take this binary mask, do some post-processing to produce like these building polygons, and these polygons then go into the Open Buildings dataset. We don't train our models from scratch, obviously. We build on top of a remote sensing foundational model. This model was trained on a vast amount of unlabeled satellite imagery in a self-supervised manner. And those of you familiar, so we use, among many techniques, we use this thing called masked autoencoder, where the idea is you take an image, you mask out bits of the image, and make the model kind of like fill in those missing bits. And in doing so, the model kind of understands the domain and learns about satellite images and so on. And the reason we do this, the reason we build on top of these foundation models is it allows you to be very data efficient during training. So if you were to start from scratch, you need a lot more data than when you actually use one of these foundational models, because the model has already learned a lot about the domain, right? So you need to just like fine tune a bit for the downstream task. Okay, so now that you've collected the training data, you've trained the model. How do you take that model and produce something like the open buildings data set? In other words, how do you scale this model at a continent scale? And here you have to have these two key ingredients. So the one is you have to have a vast collection of satellite imagery, and the second one is you have to have a lot of compute. And if you have either of these key ingredients missing, then you can't produce something like the open buildings data set. Fortunately for us at Google, we have both of these that enabled us to create something like the open buildings. Yeah, so before I go into Sky, I just wanted to say the project that was born out of Accra, we're now able to scale that outside of Africa to Latin America, Caribbean, as I mentioned, and also parts of Asia. So let's move to Sky. So now we're going from detecting buildings to detecting damaged buildings. Right, so the motivation is, we all know that the natural disasters, they claim countless lives and cause enormous economic damage every year. In 2017, in the US alone, natural disasters, weather-related natural disasters, were responsible for $300 billion worth of economic damage. And annually, natural disasters displace 20 million people globally. And obviously, this is only going to get worse with climate change, right? And when a disaster hits, it takes weeks, if not months, as Rita mentioned, to do damage assessment manually. But then the critical decisions around things like rescue efforts and aid distribution and so on has to happen within, days, if not hours, after a disaster has struck. And Sky project aims to kind of bridge this gap by using AI models. And the goal here is threefold. It's speed, accuracy, and scale. And this, if you can do this damage assessment faster, accurately, and at scale, it saves lives, and it also maximizes this humanitarian resources, which is, tighter and tighter, especially in these times. So how does it work under the hood? You've probably already seen this in Rito's talk. So we first acquire pre- and post-disaster high-resolution satellite image. And then we do this high-level assessment at a tile level. And a tile is, give or take, 200 by 200 meters on the ground. And we create this heat map to prioritize data collection to train a downstream model to do damage assessment at a lot finer detail, so at an individual building level. And for this, we use these VLM models. So these are vision language models. If you're not familiar with these, I would think this is overly simplified, but think of this as a model that takes a pair of image and text, and it outputs a score. And the score is going to be high if the text describes the content of the image, and it's going to be low otherwise. So if the image has a cat and the text says dog, the score is going to be low, right? But it says cat or, I don't know, feline creature or something, then it's going to be high. And we use this to do this kind of heat map generation. So we compare each tile of satellite image with terms like destroyed buildings or uncollapsed roofs and so on. To get the score, we aggregate the score at a high, like at a disaster area level to create this heat map. And once we have this heat map, we then run the building detection model to get the building polygons. And this is going to be on the pre-disaster image, right? Because it's hard to detect buildings on a post-disaster image. So we do this on pre-disaster image. And we send these, so once we've sampled from these areas of high damage, we then send those building polygons to our annotators to label the data. And the annotators get three things. So they get the pre-disaster image, post-disaster image, and a building polygon, and they assign a label, damaged, undamaged, or some grades of damages, right? Minor, major, and so on. So once we have the data, we train a classification model And obviously we iterate, depending on the quality bar, we might have to generate more data and so on. During deployment, it's the same exercise. You need these three things: pre, post images, and building detections. All right, so let's shift gears a bit, and I'm going to talk now about what the future of disaster response might look like, especially in the age of LLMs and agents. We know that they have a potential, big potential. You might disagree with it, yeah. So let's see how they might potentially change the field of disaster planning and response. So imagine you're a crisis response planner in charge of planning for a hurricane that's about to make a landfall in a few days. Now, as a planner, you have to juggle multiple different models. You might have to pull in data from different data sources. You might have to build very complex pipelines. So you have to synthesize all that information that's available to you at a given time. And as you can imagine, it's a very technical process. It's very time consuming. And you know, in these situations, like every minute counts, right? And imagine you're depending on weather forecast, and the forecasts change. Now you have to redo this whole thing all over again, which is quite tedious and time consuming. But now, what if you could ask a frontier model like Gemini to do this whole orchestration for you? And what if I told you this is not a science fiction but a reality already? So earlier last year we announced Google Earth AI. It is an agentic framework. So where we coupled Gemini's reasoning capability with a bunch of state-of-the-art, very specialized models, many of them geospatial models, and different planetary data sets, and created this collaborative agent, a companion that is capable of solving very complex multimodal geospatial tasks. So let's look into this quick demo. Sorry for the video, but I thought it would describe it best.
Let's examine a real scenario that requires data and analysis from multiple models. Suppose we are acting as a crisis resilience analyst and trying to understand and coordinate resources around a disaster. We'll ask the agent to predict when Hurricane Helena will make landfall using Google's cyclone prediction model. The reasoning agent generates code to access the model and places the forecast results on the map. The agent understands our goal, so when we ask about vulnerable populations, geospatial reasoning retrieves data from third-party sources like data comments, then joins and filters that data based on the previous queries and results. When we follow up with a question about risk, the agent pulls in the right data, automatically and correctly filtered. Whether it's cyclones, floods, weather, or predictive time series analysis from business data, layering in data and conducting rapid assessments decreases the time to critical decisions. Geospatial reasoning agents are collaborative companions that can give advice and understand their own capabilities. They can process abstract concepts like population vulnerability and choose the best path to a solution. They'll even explain their rationale at each step as they organize and join multiple data sets and variables. Applying models and reasoning about data is just the first step. The agent can also generate its own advanced computations and statistics. Sometimes solving problems requires fine-grained data that simply isn't available. Google Earth AI's foundation models use embeddings to up-res data and make predictions in higher fidelity. In this example, we've asked for zip code level vulnerability data, but only have county level data. To provide this, the agent calls Earth AI's population dynamics model, which generates zip code level results from its embeddings. The agent also triangulates across dozens of datasets for advanced insights. Geospatial reasoning can also understand and analyze satellite imagery. For example, with object detection, we can identify critical infrastructure. With satellite imagery-based classification, we can identify regions that fit our criteria. And with image retrieval, we can deliver collections of regions to integrate into workflows and decision-making. In post-disaster analysis, we rely on the agent to do even more complex analysis, discovering correlations between variables and plotting results. This powerful combination of Google's state-of-the-art models, on-demand data, image understanding, and generative computation and modeling is the heart of Earth AI.
All right. Yeah. So we're currently in a pilot phase. We're testing and refining our models with the help of our select partners. We're tremendously excited about the future of this tech. Please stay tuned. Thank you. And if any of this sounds relevant for your work, let's chat afterwards. Thank you.
Thanks so much, Krishna and Rito, for leading us through the underpinnings of all of this work. I think if this shows one thing is that AI adoption, making models that serve humanity and then bringing them into adoption is tremendously complex, and will also stay that way for at least some time. And we are always searching for new and additional partners to help us bringing this kind of over the finish line in more and more areas. So please be in touch. Come over to a booth where colleagues will be around today in the hall next door at AI for Good. And of course, please be in touch. Let us know what you think. We are always interested in feedback and other ideas where to bring this. If you have interest in adopting solutions or adding to our pipeline of use cases in the future, let us know. But for now, thank you so much for joining us for this session. Have a fantastic day ahead, and we will see you around. Thank you.